Whoa. Whoa. This works. Whoa. 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 Oh. One. Okay, good morning everyone. I think it's time to start our class. So first of all, I found this one. This thing starts working. Right now it's really good. Previously, it never worked. Now at least I can effortlessly increase the voice. Okay, so first of all, we have released homework 4 on last Thursday. And based on what I have discussed so far, you should be well prepared to implement everything in homework 4. That's really concentrated on support vector machines. So we have discussed the primal training of support vector machines. What's the dual form, how to simplify the dual form, and how to solve the dual form and then recover the optimal weight parameters and bias parameters from the dual form results. Of course, we need to leverage some conclusion concepts in optimization theory, which is called KKT conditions. Well, although we have introduced several basic concepts and facts, looks like a bit more mathematical notations, but they are not hard. What we need to do is just based on these facts, get to know how can we recover the weight parameters and bias parameters from the dual solution. Right? So in our homework 4, there's one problem asking you to write down the whole reasoning logic. So that's actually to request you to review our slides. If you haven't taken our lecture, you can watch the lecture video and led through the and being led by our discussion. It's fairly easy to get clear about the details, right? And but do not copy and paste. Do not copy the slides. Do not copy everything from slides. Write down at home. Understand. If you carefully down that problem, there won't be any issue for you to understand SVM, also the implementation. And also our PM, Shikai, has given, I believe, an excellent tutorial about how to leverage Python libraries, especially SciPy and NumPy libraries. That will be very, very helpful for you to not only implement SVM, but also for your future explorations with Pythons, right? Like you can, to solve SVM view, you don't need to write the optimization algorithm yourself. You can call some SciPy optimization library, and I think Shikai's guidance will be helpful and help you to identify which particular API I should use and what kind of examples I can test. Right? They are all contained in the online documentation. Right? Hopefully it helps. Again, I will highly recommend you to start doing homework 4 right now. The workload is lighter as compared with the previous homework assignments, but you do need to understand the whole idea about SVM, and you do need some time to test your implementation and to make sure that your learning result is reasonable. So again, please leverage the office hours. Right? Our office hours still are quite empty, right? And basically that's it. And before we wrap up SVM, I want to again clarify a bit more details in case some students will stuck in some, minor things. Although we have discussed and stressed on them before, but the thing is I'm going to clarify again is the common issues where previous students have met. So I don't want you to suffer from the same pitfalls. So I want to emphasize again. Okay. First of all, we have discussed in last week, right? So if we want to extend our SVM to be capable of doing nonlinear classification, we need to seek for the dual form. Why? Because in the dual form, it is easy to inject the kernel trait. Right? So imagine here the whole idea to extend linear classifiers, nonlinear classifiers, is to perform some nonlinear feature mapping first, right? So in our original feature space, all your data is hard to be separated linearly. But you can imagine after some smart nonlinear transformation in a mapped feature space, those data will be much more regular, right? And you can imagine there is a big hyperplane which can well separate the examples in a new feature space. So However, this new feature space usually is very high dimensional. Right? When we talked about the kernel trick last week, right? We gave an example. It's called Gaussian kernel. So the Gaussian kernel actually corresponds to an infinite dimensional feature mapping. So basically, you can imagine there is an infinite feature space where through this kind of nonlinear feature mapping, your all the points are represented by an infinite dimensional vector. Well, in theory, although you can still find a hyperplane to separate those points very well, right? But in practice, you'll never be able to explicitly compute an infinite dimensional representation of your data points. Right? So, to extend our linear classifiers to perform nonlinear classification, our first priority is to avoid performing explicit feature mapping. We don't want to do that. And the trick is called kernel trick. Kernel trick can compute the inner product of the mapped feature vectors in the original feature space. You don't need to perform any explicit feature mapping. Right? In so doing, your computational cost will be dramatically reduced. Right? So if you look at the dual form of SVMs, right? So it's a quadratic minimization problem, right? Why? Because it's a double summation, where in each summand it's a product of paired examples yi, yj, and alpha i after j, and then the inner product between a pair of the training inputs xi, xj, right? So alpha i's are the variables we want to optimize in solving the dual form, right? So those yi, yj, and xi and xj are actually constant. Right? So this formulation obviously also apply to nonlinear feature mapping. Right? Suppose you perform some feature mapping first, and then you solve this dual form, then this xi transpose xj will be replaced by phi of xi transpose of phi xj, right? Because you need to operate everything in a mapped feature space. That means you need to represent those data points by the mapped feature vector. The mapping function is denoted by phi, right? So to avoid explicit computation, right, we can inject kernel trick. So this inner product after feature mapping can be directly calculated by this kernel function, right? And this kernel function, it just calculates the function of the original inputs. So it is expected to much cheaper. And another major benefit is that doing so, you never need to change anything in the optimization procedure. Why? Why you don't need to modify your optimization algorithm? Yes, I do.
Can you solve for alpha?
Yes, exactly, right? So remember, our optimal variables we want to optimize are just alpha i's, right? They're essentially the Lagrange multipliers. So all the other things are just constant. So you just replace this inner product constant by this kernel function constant. Nothing else is changed. So you just run the same quadratic optimization algorithm. Right? You can use from Python SciPy library or R library or MATLAB default function, whatever you want. Nothing is changed. Right? So solving the dual is essentially to solve this optimization problem. You get alpha and alpha j, right? And during the prediction, as we emphasized a moment ago, right? We never want to explicitly compute the optimal weight vector, because in a mapped feature space, the optimal weight vector can be very, very high dimensional. Right? The weight vector in a mapped feature space should have the same length as the mapped feature vector. Right? So, take an extreme case. Suppose you're doing an infinite dimensional feature mapping. Well, your W in that space will be infinite dimensional. Right? It's never practical for you to calculate an infinite dimensional vector. So we're going to leverage the structure of the optimal weight vector. Right? this is derived from our previously, right? When we simplify the dual form, and we can derive that the W can be represented as a linear combination of the input vectors, training input vectors, weighted by those alpha i's. Right? Of course, after Fisher mapping, you need to calculate you need to represent W in the mapped feature space. So this xi is going to be replaced by the mapped feature vectors. So now you just substitute this structure for W star. In the prediction score, you get the inner product between the W vector and the mapped feature vector for new task input is this summation, right? So the summation, again, is summation over all the training examples and weighted by alpha I star and yi, and then you have to calculate the inner product between every training example and the task input. Right? Of course, after feature mapping, you need to first do the feature mapping and do the inner product. And again, to avoid naive completions in the product, we're going to replace it with our current function. Right? That's how we perform the prediction step. You can see that in both training and prediction step, we never conduct any explicit feature mapping because we know that it is very expensive, sometimes even infeasible. So the remaining question would be, how can we identify B, right? The bounds parameter, because we're solving the dual form, when we solve this, right? All we know is just this optimal Lagrange multipliers alpha I stars. Right? And we talked about in a linear case, right? If we do not perform any feature mapping, we can directly recover W star by this combination, right? And then the problem how to recover B. Right? We discussed in the previous lecture, right? The way to recover B is exactly the same as in the linear case, right? And the only difference is that you're gonna replace this inner product between the weight vector and the mapped feature vector by this, right? And also this. But I want to give it to make it more explicit in case that someone might still feel confused. Right? So remember when we talk about the linear case, if we want to recover the optimal bias parameter B, how can we do that? We're going to leverage the complementary slackness from the KKT conditions and also result when we optimize the dual solution. Right? Then those results tells us to recover B, we can find some example J. The corresponding optimal alpha J is strictly between 0 and 6. Right? And then following these three types of conclusions, we can get that the functional margin of the example J will be exactly 1. Right? I'm going to ignore how we derive this. I will leave it as your homework to review. Right? So then to get the optimal bias parameter B, we can subtract the label, for example, J, by the inner product of the optimal weight vector and the input vector xj, right? That's in a linear case how we recover B star. Of course, if you have multiple such examples whose alpha J star is strictly between 0 and 6, you can estimate multiple B star and take an average to make the estimation more reliable, right? More robust. But in a kernel case, how can we do that? Right? If we perform some very high dimensional feature matching, right? How can we obtain B star? Any thought? Yeah, think about it because you have to implement nonlinear SVM. You need to write a code to get B star and then plug them into the prediction function to make predictions for new examples. How do you get B star?
Just the same way we were doing it before, except xj instead of x.
Yeah, exactly, right? Just look at here, right? Of course, when you perform some feature mapping in a very high dimensional, even infinite dimensional feature space, I don't want to exactly compute W star. I don't want to explicitly compute W star. I don't want to explicitly compute phi of xg, the mapped feature vector, right? So I want to use kernel trick, right? This is the same trick as we used during the prediction step. This inner product is essentially can be written as a summation over all the training examples, where each summon is just alpha I or I, and then the kernel function between the example, training example xi and test example x. The same thing here, right? Except that you're going to replace xj. You're going to replace x by xj. That's it. And then you get b. So now hopefully these are kind of very detailed enough for you to implement non-linear version as well. So hopefully no one is gonna be stuck here. Okay, any questions so far? Is everyone comfortable with SVM stuff? Okay, great. So last thing I want to clarify is that the position of the non-support vectors. So last lecture we showcased where the positions of the support vectors come from. Right? What are support vectors? Can you recall?
Non-zero alpha.
Yes, exactly right. So remember W, the optimal W is essentially weighted combination of all the training examples, right? And of course, if some alpha I star is 0, that example won't have any influence on the optimal weight vector, right? Sorry, it's a silly Siri app. So, of course, W star from this structure, W star is only determined by a subset of examples whose alpha R star is non-zero, right? For 0 alpha I values, those examples are called non-support vectors. So we mentioned that the position of non-support vectors will be strictly outside margin, right? That means I asked you to consider that and think about why. This is an exercise, right? But here, just to give you the answer, hopefully you have thought about that. So, for non-support vectors, they're going to stay outside margin, right? So if they stay outside margin, that means the function margin must be bigger than 1. So that means this part, this is the definition of function margin. Yi times the prediction score. This function margin is bigger than 1. So this function margin is subtracted by 1, then plus this non-active slack variable will be strictly bigger than 0, right? If you just look at this, like the function margin is bigger than 1, then this term, this whole constraint function inside this parenthesis is strictly bigger than 0. And according to complementary slackness, this product must be 0. Then there's always one conclusion: the alpha I star must be 0. So that explains why all the vectors, all the points which stay strictly outside margin will be non-support vectors. Okay. So I highly suggest you to, okay, any questions so far before I throw out my suggestion? Is everyone comfortable with that? So I highly suggest you to go through the content listing of lecture slides. They are self-contained. No need to double check with other textbooks. If you want to learn more in depth about optimization theory, all kinds of discussions, you are welcome to do so. But if you just want to know the key ideas and the details about SVM, our lecture slides are enough. And we highly encourage you to go through lecture slides and to understand how those basic facts are smartly combined to derive all those results, and all these alpha I values and beta values and slack variables determine the positions of the support vectors and so on. These are really helpful to have. This will be really helpful for you to get deeper understanding of SVM. Okay. Okay. Any question regarding SVM? Great. So now let us talk about an important practical trick in tuning hyperparameters. We decide to introduce this trick right after SVM because SVM is a prominent example. Okay. So this is called cross-validation. So in general, cross-validation is seen as a model selection approach, and it is used very, very broadly, like in many machine learning applications. You can see the application of cross-validation. Why? Because in your machine learning model, in addition to the parameters which you want to estimate from data, you always need to set some hyperparameters, like the number of training epochs, right? The number of epochs used in perceptron, also in SVM, the trade-off between the regularizor and the hinge loss. So those parameters, unfortunately, are not able to be optimized through some objective function. You see that later. Right? And then we can come out an easy but effective way to identify such parameters. So we can think about, in general, what makes the machine learning model. So to determine a machine learning model, you need to give three things. First, you need to prepare training data. Right? Without training data, well, you don't have any clue about which, how to specify those parameters to make it work properly. Right? That's very, very important, sure. And also, the loss function. Right? The loss function actually measures how your current model fits the training data, right? If it do not fit well, or you're gonna need to adjust your model parameters, like through gradient descent or stochastic gradient descent or mistake-driven update, whatever. You want to make your model better and better fit the training data, right? But in addition to that, there are also hyperparameters. So what hyperparameters do we have? Number of epochs in perception. Okay. So when you implemented your multiple perception, average perception, you always need to set, okay, how many epochs I'm gonna go through the data. Okay. And there, this big T, right? We use big T to denote the number of epochs. Right? This big T never appears in any loss function or objective function. You cannot optimize it using gradient descent. Another hyperparameter is C in SVM. So what does C mean?
The parameter that controls the trade-off between margin and minimum flag.
Yeah, exactly, right? So appreciate that you guys still have a good impression about the definition of C, right? So let me just write down although C appears in our objective function, but you see that we cannot direct optimize it. So to clarify this, like let me write down the objective function for SVM. Right? So we know it is a regularizer. This regularizer, remember, it encourages large margins, right? And large margins corresponds to a smaller hypothesis spaces and smaller BC dimension, right? And then plus C times the hinge loss, right? So these are loss of generality. I just write them down as per. Suppose you have big N 10 examples. The hinge loss is max 0, 1 minus the function margin, right? So it's Yn W transpose Xn plus B. So we want to minimize this objective function in terms of W and B, right? But now we also need to set up this C, right? C indicates the trade-off between the regularizer and the hinge loss. The hinge loss actually indicates the null fit of data. Remember, this is from the computational learning theory. In Gaussian learning, we have a generalization error bound. This true error is upper bounded by the training error plus some term determined by the BC dimension, right? Okay. This is structure, right? So this part, the hinge loss corresponds to the training error, and this regularizer corresponds to the BC dimension. Right? We want to find a trade-off between the two, so such that you got a smaller, you got a smaller generalization. You got a generalization error bound as small as possible. Right? So now I want to ask, how to set up group C? Can we jointly optimize this whole objective function with respect to C as well? Like previously, we assume, okay, C is given fixed, right? We already optimize W and B, right? But now, I want to jointly optimize W, B, and also C to make this whole objective to be minimal. Is it feasible or is it reasonable? Any thought or any guess? Any comment? Yeah, we can definitely directly do this, right? We can directly minimizing this objective function with respect to W, B, and C. But will the result be something we want? I saw someone say,
No, it could allow for C to like wipe out one of your terms.
Yes, exactly right. So, I mean, from the action perspective, you can do that. But let's see what will happen if you do this. So, remember, C is always non-negative. We cannot let C to be negative, because if it's negative, there's nothing. You cannot say it's a trade-off. It's just a is a non-negative C, right? If you want to minimize this summation, remember, the hinge loss is always non-negative, right? So if you want to minimize this whole objective with respect to C, what will be the optimal value of C? 0, right? Someone has pointed out. That means C will simply be 0. Will C being 0 be a good choice? Obviously not, right? Remember, our generalization error bound is a trade-off between you know, the training error and the regularizer, right? So if you let C to be 0, that means, okay, you can allow training error to be arbitrarily large, right? Although you can minimize this one, right? But actually, a much bigger training error won't give you any benefit to get better generalization. So obviously, C is 0 is not a good choice. Then a natural question arises, right? How can I choose C? Obviously, even this C shows up in the objective function and seems that it can be jointly optimized with our model parameters. We shouldn't do that because that will lead to very bad consequences. So that's why we usually differentiate C and other model parameters. We call C a hyperparameter rather than another parameter, because we need to select that in a different way. Not to mention other hyperparameters like number of epochs, like learning rate, those kind of stuff, even is not showing up in the objective function. So then what is the general idea to select those hyperparameters? Well, cross-validation is a very common use one. So what is cross-validation? So the idea is pretty straightforward. I'm going to first choose a set of candidate values for C. So suppose I believe the best C should be selected from like 0.01, 0.1, 1, 5, 10, even 100, right? So, but I just don't know which one will give me the best performance. So I need to check the performance of reusing each C value and then determine which one has the best performance. For example, if C equals to 5 turns out to make the training and the testing performance best, I'm going to use C equals to 1, C equals to 5. Then the question is reduced to how can we evaluate the performance of each candidate value of C. Then we're going to use the cross-validation. Or specifically, this is usually referred to as the k-fold cross-validation. Why it's called k-fold? We usually split the data into k parts, right? Each part is of equal size. You can imagine like you randomly shuffle the data, then you partition the data into 5 parts, right? Each part consists of the same number of training examples. Then, at each step, we're going to use one part for test. This part we call it a validation data set, and use the remaining parts for training. We use the remaining parts to train our model with this given C value, and then test the training model on the validation set. So we got one accuracy. So for example, if we first use part 5 as our validation set, then we use the first 4 parts as our training set. Then we just train our SVM with our C value, C 0.1, right? And then after training, we just test the performance of the validation set part 5. We got one accuracy measurement, which we denoted by accuracy 5. This is not sufficient because this is just one split of training test set. It's not, the result may not be representative, right? To get a more reliable estimate of the performance using our C candidate value, right? We're gonna switch to next part, say part 4. We use that as a validation set. Again, use the remaining parts, like part 1, 2, 3, and 5, as our training set. And we train our SVM with that C value. And then test the trained SVM on part 4 to get another accuracy value. Right? you continue this, right? Then you switch part 3 and use that as my validation set. Then use the remaining parts to train SVM. Use this given C value, right? And then test the trained model on part 3. You get accuracy 3. Continue this until you have used every part as the validation set. You got the training and test accuracy, right? So finally, we average all those accuracy measurements as our ultimate performance measurement for this particular C value. Okay. Doing this can help us know what's the performance of using one candidate value. Okay. Now you're going to proceed to the next candidate value and do the same procedure again. Same k-fold cross-validation again. You get performance measurement for another candidate value. Suppose you have 10 candidate values, you do 10 k-fold cross-validations, you got 10 performance measurements, right? And then you just pick up the one who has the best performance. That's how you select the hyperparameters with cross-validation. Any questions so far?
So we have like k-1 test set. Do we consider them combined for the testing or like each?
You actually have k test sets.
Sorry, k-1 training test.
Yeah.
So do we consider them combined for the training or like one by one?
Combined. Like you got part 5 as the validation set, right?
So
then you combine all the remaining parts as a whole training set.
okay.
And then you train SVM, then you test on part 5, you get 100%.
So you test it on part 5, the remaining is trained.
Yes. Any other question? Okay, great. So let me represent the whole procedure in terms of algorithm framework. It will be very easy to follow when you try to tune the hyperparameters in your SVM implementation, right? So for any given hyperparameter value, right, you're going to first split the data into k equal size parts, and k is usually chosen as 5 or 10. Then you train a classifier on t-1 parts, and then evaluate on the remaining one. You repeat this using each of the k parts as the validation set. Then after you have done this, right, the quality of this hyperparameter is average of this k estimates. So you get performance measurement for this particular hyperparameter, and of course you need to repeat for every hyperparameter choice. And finally, you pick up the one who has the best performance. And once you pick the best hyperparameters according to the cross-validation procedure, you're going to retrain a model. Why? Because the previous evaluation is just a partial data set, right? If you use 5-fold cross-validation, every time you only use 4/5 training set for the evaluation, right? Now that I have known which hyperparameter is the best, I'm going to retrain the model on the full data set. Use this best hyperparameter. And then I perform my evaluation on any new examples. So this is a very straightforward but a very widely used approach. The benefit is that, okay, you don't need to care about the type of hyperparameters. Right? It can be discrete, it can be continuous, it can be whatever you want. Like for example, later we're going to talk about artificial neural nets. A very important hyperparameter about our neural networks is the architecture. How many neurons per layer you should use, how many depths you should choose, and what kind of activation functions, right? Those are discrete. They're all discrete variables. And what you need to do is just set up a range, which set of depths and width and also type of activation functions are of your interest. Then you just conduct cross-validation to choose the best one. Yeah, homework 4, you are requested to apply the cross-validation to identify the best hyperparameter C on the specific data I will give you. Okay, any question regarding cross-validation?
We have to do a cross-validation on full data set or a part of our data set.
What do you mean by full data set?
For example, we have 100 row and 10 features for each row. We should do, and this is the training set. We should do it on whole this training set, or just use 20 of this.
No, on a whole training set. But don't use test set. For example, you have like 200 training examples in total, right? I'm gonna select the best hyperparameter based on these 200 training examples. How can I do that? I'm gonna partition these 200 training examples into, say, 5 folds, right? 5 parts, and then I'm going through each part using it as a validation set, and then use the remaining parts as the training set. But this training set is not the whole training set. And then evaluate. Other question? Great. So now let us switch back to our PowerPoint slides. So, starting today, we're going to spend quite a few lectures introducing a very powerful and very popular type of machine learning models, neural networks. Right? Nowadays, when people talk about artificial intelligence, most of the time they're referring to artificial neural nets. They're referring to machine learning and artificial neural nets, right? So you can see how powerful neural networks are. Right? So, but it's worth knowing that our neural networks are not like brand new techniques. All the key technologies of neural networks were invented about 3 decades ago, no, 4 decades ago, even older than me. So right now, neural networks kind of become dominant again. And mostly because under the scenario of big data, the neural networks experience surprising power in a lot of applications, like image classification, like autonomous driving, all kinds of stuff. If you take a look, if you have a chance, you can take a look at some video released by Tesla. Their autonomous driving system is really impressive. And you can see that when the camera, they only use like very naive, it's not very complex radar. It's just macro view radar, if my recollection is correct. Right? And the major components are just the cameras. When they look at when the cameras capture the images, they have some neural network implemented in their chips. And those neural networks are so powerful, it can actually capture every signs and pedestrians and construction signs, all kinds of stuff. It's very, very impressive. So I highly suggest you to take a look at that. It indeed demonstrates this network modeling why it's so powerful. But why it is so powerful? Right now, people don't have the kind of like a good answer to that. Like, people just found out, okay, if I do it layer by layer and activation, nonlinear transformation, those kind of serious transformations, it can make my model to be very, very expensive. But why? No one knows. Okay, so before we talk about neural nets, we just want to step back a little bit to organize what we have seen so far. Right? And so we have seen quite a few learning algorithms, right? Decision trees, data boost, bagging, perception, support vector machines, and so on. Right? And throughout our discussion, we also introduced several general learning principles, like the idea of overfitting, mystic bound learning, which supports how we train perception, right? Path learning and basic dimension and generalization, error bound, all kinds of stuff. So we spent quite a lot of time talking about linear classifier, right? Of course, someone might be unsatisfied because real world are really complex. Right? You cannot expect your linear classifiers, your linear assumption work everywhere. Naturally, we want our models, our algorithm are capable of handling nonlinear cases. So our very first strategy is to apply some feature mapping and then kernel trick. Right? The benefit is that, okay, all those tricks are based on existing linear classifiers. Right? So you don't need to change much about the learning algorithm. So all you need to do is just combine some advanced computational trick like kernel trick to avoid explicit feature mapping. That's it. Right? But of course, there is naturally another idea. Right? Why should I build up my nonlinear classifiers based upon linear classifiers? Why not we construct a nonlinear classifier from scratch? So neural network is the second strategy. We want to just construct very powerful, very expressive nonlinear classifier, nonlinear regressive. That's about neural network. Okay, so the topic about neural networks will consist of following four points. So first, we're going to give the definition of neural nets. Right? What kind of machine learning model can be called a neural network? We're going to talk about the hypothesis basis, right? And also which determine a neural network, right? Why it is so expressive. Right? And then we're going to talk about the rule to make a prediction with neural network. Actually, even your network structure is given, your model parameter given, if you want to make a prediction, you have to follow some particular rule. This is called forward pass. Okay? And then our major concentration will be in the training part, because it's the creating part. Right? So we're going to talk about the essential techniques in neural network training, which is called backpropagation. You see that nearly every modern neural networks, their training is based upon the backpropagation, and invented about in 1980s, about 40 years ago. And everyone is required to implement your own backpropagation, and then test it on real data, and to demonstrate that your backpropagation works. Okay? And finally, we're going to talk about some practical concerns about using neural network. Neural network is amazing, but it's not the God. It has many issues, and you might have many problems in using that. So these are just some suggestions when you apply neural network in practice. Okay. So to introduce neural network, we're going to start with the linear threshold unit. Right? So linear threshold unit, we actually have discussed it when we talk about linear classifiers, right? Linear threshold unit is viewed as a graphical representation of linear classifier. So suppose you got 4 features from the data, right? X1 to X4, and then we're going to first collect those feature values, right? Those are information. Right? We'll collect those information and aggregate them into some intermediate node. Right? How can we do that? We graphically, right? We just connect the input feature to this intermediate node. On the edge, we attach a weight. That basically says, okay, I'm going to amplify the incoming message, right, by the corresponding weight. So this intermediate node will receive x1 times w1, x2 times w2, x3 times w3, x4 times w4. And also we're going to augment a constant feature 1 and then put an extra weight b here. So this intermediate node will also receive 1 times b. So then we simply add up all the incoming messages together. That's where this summation operator stay here. Right? Means we're gonna sum up all the incoming messages. So then the result will serve as the output of this intermediate node. So you can see that the output is essentially calculated by W1x1 plus W2x2 plus W3x3 plus W4x4 plus b times 1. Right? This is essentially to do the dot product. Right? If you view the whole input features as one vector, all the weights and bias parameter attached on the edges as another vector, this is essentially to do the dot product between the two vectors. Right? And then the output of this intermediate node will be sent to a second node. And then we're going to perform some thresholding transformation as our output. And this output is actually the label of our linear classifier. Right? So you know that if you feed your features through this linear threshold unit, the output is essentially this. Right? Any questions so far? Right? We have discussed this before. Why not just review it? So, and the learning of the linear threshold units is essentially to identify the weights on the edges, right? So we have talked about a variety of algorithms like perceptron, like SVM. We can come out any loss functions and regularizer to identify them from the data. So now, build upon this, we want to extend capability. Right? We want to build up a model which is much more powerful, which can deal with all kinds of nonlinear cases. The idea is to use this as the basic unit, like you construct a house or construct whatever apartment, right? You need to prepare some basic units like bricks. So you can just use this single threshold unit as one brick. Right? Now we're gonna attach them together, concatenate them together, and put them layer by layer. Then you get your guy. And interestingly, even by several simple rules to combine them together, you end up with very powerful nonlinear classifiers. Okay, so how can we create more expressive neural network based upon this single linear threshold unit? The idea is that, okay, I'm not assuming the inputs of my linear threshold units are directly from data. Instead, we're assuming the inputs coming from the output of other linear threshold units. So, suppose we place our original data here, right? And then we construct a set of lower level linear threshold units. Right? The output of the first lower level linear threshold units will serve as input of our final linear threshold unit. Okay? And the output of second level linear threshold unit serves as input of our second input of our final linear threshold unit. And you continue to do so, you actually construct 4 more lower level linear threshold units. Right? Their outputs are served as input of our final or higher level linear threshold units. And of course, to differentiate different linear threshold units, the weights and biases attached on those edges are totally different. In so doing, we actually have constructed a two-layer feed-forward neural network. And the rightmost one is called alpha layer. Why? Because the output of this two nodes is our final prediction, right? And the layer in the middle, the nodes in the middle, is called hidden layer. Because we do not directly observe them from data, we need to do some kind of linear threshold computation together. Right? And the leftmost one are directly from data, so they are called input layer. So there are in total 3 layers, but according to neural network literature, we usually do not count the input layer. So we call it 2-layer feed-forward neural network, because the input layer is known. So you can view the hidden layer as essentially some kind of transformation of the input data, right? So this one is one particular type of feature matching, right? The second one is another particular type of feature matching. Third feature matching. Fourth feature matching. So some people, in the kernel learning community, you just will neural network as a particular type of feature matching. But neural network people won't see that. They don't like to be viewed as a special instance of kernel learning. But there are some connections. So, oh, by the way, any questions so far about how to construct this neural network? Okay. Is everyone comfortable? Okay. So, for convenience, we don't want to explicitly write down 2 nodes. Right? We're gonna merge these 2 operations together. That is, when we have these incoming messages, right? They're gonna multiply by the weights on the edges, and then we first do a summation, then perform some transformation. Here is the thresholding transformation. We do these operations together. We call this result as a neuron. So we actually merge the 2 nodes together. We call this merged node as a neuron. And to get onto the neuron, we're going to first do the summation and then perform some transformation. So this is called neuron. In this way, our 2-layer feed-forward neural network will contain 1, 2, 3, 4, 5 neurons, right? And 4 neurons in the hidden layer and 1 neuron in the alpha layer. So, of course, if you want to make even more expressive, even more complicated neural network, we can further assume this x1, x3, x2, x3, x4 are the outputs from an actual layer of the linear threshold units. In this way, you can construct 3-layer neural network, you can construct 4-layer neural network, you can construct as many layers as you want. If you have many layers, this is called a deep neural network, or deep model. That's where the deep comes from. And I can give you a sense, like the very powerful and very successful image classification model, the number of layers can be like 256. There's a very famous network called ResNet. You can check out 256. Okay, so here we have given some kind of intuitive idea how to construct neural network. Right? Now let's try to formalize this. Right? So in general, neural networks are a type of very robust approach to approximate real value, discrete value, or vector value functions. You see that the theory tells us that neural networks are very powerful function approximators. And they are among the most effective general purpose supervised learning current known, especially for complex and hard to interpret data, such as image data, such as voice data, such as sensor data, video data, etc. And the K for neural networks is the backpropagation algorithm, which will be the major focus of our discussion. So neural networks, their invention are enlightened from the biological neurons. So, so this is just a fundamental knowledge. I'm not expert of biological neurons. Just to give you a hint is that for like nerve system, the basic components are indeed neurons, and neurons will consist of the so-called dendrites and axons of dendrites. It's just like to collect information from other neurons. And axons are kind of like a postman. You try to send out this message to other neurons. And the message is really kind of like spikies, electrical signals and spikies. And neural network, they're developed to make some analogy for the biological neurons, but don't take it seriously. Because a serious biologists, especially for neuroscience, they won't admit any similarity between artificial neural nets and the real neural nets. They're just a kind of conceptual analogy. And a group of researchers, actually I have met them, discussed with them several years ago in Google. They try to simulate real neural networks. They want to incorporate the critical properties of the real neural nets to get their own artificial neural network, and then test their own artificial neural nets on a few benchmark data sets. It turns out to be worse than the current neural network. So you can see there's a huge gap between the biology research and artificial intelligence. Okay. So, like biological neurons, like artificial neurons, artificial networks also are consist of artificial neurons, right? But what's the mechanism of an artificial neuron? You can view it as some kind of function, very loosely mimic a biological neuron. Right? So it accepts a collection of inputs, which usually, for convenience, is denoted by vector x, then it produces an output by two steps. So first, this neuron will apply a dot product with the weight w and the input vector x, then plus a bias parameter b. And then we'll apply a transformation, which is called activation. And this transformation is usually chosen to be nonlinear. So the computation procedure of a neuron can be summarized as this simple formula. This is incoming inputs or incoming messages from other neurons. You do some dot product with a v vector w plus a bias parameter b, and then apply some nonlinear activation function. You get the output of that neuron. And one particular example is the linear threshold unit, right? And here, the activation is the thresholding function, right? It's a sine function. Take the sine. Right? And of course, you got a lot of choices of activation functions. Like the simplest one is called linear unit. Basically saying you are not performing any activation. You just take the original input C. And also this is a sine function. Right? Another three very commonly used activation function is called sigma unit. And this sigma function essentially to squeeze the input into a range between 0 to 1. If you can do some simple analysis, you'll see, okay, this value, function value is always between 0 to 1. And rectify a linear unit. It takes maximum value between 0 and input z. And also tan h. Tan h, you kind of squeeze them to 1 as 1 and 1. Any questions so far? Is everyone good about the definition of neuron? It's just a kind of a way to operate, to calculate and integrate the inputs. Okay. Then a neural network is kind of a network that organizes a bunch of different neurons. So you can view it as a function that converts inputs to outputs defined by a directly acyclic graph. There's no cycles in the graph, right? Nodes are organized layer by layer, and each node corresponds to a neuron. And edges carry output of one neuron to another, and they are attached with weights. So here's one example, right? So this is a two-layer neural network. Those are input layer, input node, right? Those are all the neurons. So you can imagine that this neuron accepts inputs from all the inputs, right? Inputs from all the input layer, and of course each edge is attached to the weight, right? And then you multiply the weight with each incoming node value, right? Add them together and perform some activation function. You get the value of this neuron, and this neuron will send out their value to the layer above. You do this from bottom layer to the output layer, and finally got output.
Our activation function should be same in each neuron of our layer.
Oh, that's a very good question. There's no strong restriction that must be same, but in practice, almost all neural networks use the same activation function across all the neurons. But I mean, you're free to use what different activation functions for different neurons. Okay, how do we define a neural network? First, you're going to specify the structure of this graph. Namely, how many layers do you want to have, and how many nodes per layer. Then how the layers across different, how the neurons across different layers are connected. So if each layer in the current layer connects all the neurons in the previous layer, this is called a fully connected network. But of course, there are other versions, right? You can define that, okay, this neuron is connected by only 3 layers here, the 3 neurons here, this node is connected by only this 3 and this, and this 3. So it's totally up to you. So once you determine the structure of the graph, and also determine the activation function on each node, right? You can choose to use different activation function for different neurons, or you can choose to use one activation function for all the neurons. It's also up to you. And once this structure and activation functions are selected and determined, your network is defined. Then the remaining thing is to train a model to estimate the weights and the biases attached on those edges. So the training essentially is to learn the edge weights in the neural networks. Any questions so far?
Why is that cycle not so like feedback from the next level to the previous layer? So you say it's a characteristic graph, right?
Yeah.
So each layer, so can it be that like the information from the next layers can be fed back to the previous level?
Yeah, that you can do that in some special cases. I mean, for some research topic, they want to break the standard definition of neural network. You want to get some like loop message back. It is doable, but here we just talk about the standard definition. And in practice, almost all neural networks are defined that way. There is another type of neural networks called recurrent neural network. Conceptually, they have some kind of loop in that, but in practice, you see that they're always unrolled as a sequence of networks that are connected one by one. So they do not contain both. Okay, so here is just a brief history of the neural networks to give you a sense that these are not like brand new things. They have been developed a long time ago, and starting from some linear threshold units, and then some hypergroup. Hypergroup is actually the way how we update the perception, and then Perceptron is a wheel-based neural network at early stage, and then in the 1980s there is another very important type of neural networks called convolutional neural nets, which are very widely used in image data. And from 2003, this kind of like a fast and breakthrough about neural network, because people found that with big data, right now we have a capability to deal with very large data, to train very large neural nets, and with a lot of data, people have found that neural networks are really powerful in many tricky tasks, and some performance is even better than human beings, like AlphaGo, like playing AlphaGo. People never thought about computers can beat human players best players ever. And now with the help of neural nets, we can do that. Okay. We have discussed what's the general definition of neural nets, right? And it looks like you use simple rules to combine a bunch of basic units, and now it's being very powerful network. But how powerful it is? We're going to look at this we're going to check this by looking at the expressiveness of neural nets. Namely, if I construct neural network, what kind of functions it can represent, right? If it can represent all kinds of functions, means that it is really expressive. Right? If it is restricted, for example, it can only represent linear functions, well, it is still limited. Right? So, for the single neuron, like linear threshold activation function, we have discussed a lot, right? It's just a linear classifier. We know they can only represent the linear hyperplane. It's a hyperplane in high-dimensional space. Two-dimensional space is just a line, right? It's quite limited. And now, if we use this linear threshold unit as a break, right? As a basic break, and then we just build up two linear neural networks, okay? Connect them together. Then we can show that the two layer neural networks with threshold activation functions can represent arbitrary convex polygons. In that, if you use this convex polygon as your classifier, maybe all the points inside this are classified as positive, and outside classified as negative. So you can see that the classified boundary is now nonlinear, right? You just concatenate linear threshold units into two layers. Now they can represent a quite complicated nonlinear classifier, right? What about I add one more layer, right? If I construct a three-layer neural network with these linear threshold units as basic components, then it can represent arbitrary finite unions of convex polygons. Right? So it becomes even more expressive, right? So, of course, in practice, people rarely use linear threshold, use threshold as our activation function. And most often people use tanh, use ReLU, and use sigma activation function. Partly because this thresholding function is still not expressive enough. But using this as an example, I'm showing that how powerful, right? This simple rule to construct multi-layer structures can dramatically boost the expressiveness, right? The capacity of your model, right? So there's a famous theory called universal function approximation theory. It tells us any continuous function can be approximated to arbitrary accuracy just using one hidden layer of the sigma units. So basically, if you use sigma activation as your activation function, right? You just construct two-layer neural network, you have one hidden layer. As long as your hidden layer is wide enough, it can approximate any continuous function to any accuracy level 1. This is a very famous theory. It's called universal approximation theory. And this approximation error is insensitive to the choice of activation functions. Namely that you switch to other commonly used activation functions like tanh, you get the same result. So it's some kind of magic power underlying neural networks. This just talk about one data here. But in practice, as we discussed, we will have many layers. So here is just this dimension of the threshold networks. You can see the this dimension is the size of is the number of edges times the logarithm of number of edges. So you can see that when you have a wider network, you have more edges, your this dimension increases fast. And for sigmoid networks, we don't have like analytical expression of this dimension, but we have the upper bound, lower bound. You can see that the basic dimension is upper bounded by the square of number of nodes, the square of number of edges multiplied together. Right? And lower bounded is by the square of number of edges. So you can see that when you increase the layers, when you increase the number of nodes, when you increase the number of edges, it will increase the capacity of neural network. Those are just showing that neural networks can be very powerful and can be very flexible. But someone may consider, okay, it can easily overfeed data, right? Remember from computational learning theory, will tell us that the more, the larger the basic dimension, the more you're going to have overfeed data. Your generalization error bound can be suffered, right? So that's the problem. That's always the problem. No model is perfect. The benefit is that on the very large data, although you have a large basic dimension, your training error can be very, very small. But for simple model, you cannot well fit a large amount of data. So that's why neural network is often preferred in big data, because it can well fit a large amount of data. This mainly becomes from its capacity. Any questions so far? Okay, the final exercise. I want to think about it. If we use linear units, meaning that I use linear activation function. So the activation of the z is equal to z. Then no matter how many layers you perform, you are still linear classifiers. Think about that. Okay.